For decades, there have been recurring reports of objects that appear to behave in ways that challenge straightforward interpretation. Cases where rotation, field measurements, and internal readings seem to produce results that are difficult to reconcile with standard expectations. One of the more recent and controversial examples comes from an interview with researcher Rodolfo Garrido, who describes a series of experiments conducted on what is referred to as the Buga Sphere. The account centers on repeated mechanical tests performed under controlled conditions, where the object is rotated and monitored using a range of sensors designed to track weight, temperature, and electromagnetic activity. The experimental setup, as described by Garrido, involved a purpose-built industrial device. This apparatus was not simply a motorized platform, but an integrated system combining rotational control with multiple measurement layers. The sphere, initially reported to weigh between roughly 10 and 13 kilograms, is placed on a calibrated base equipped with load sensors intended to detect even small variations in mass. The system also includes thermographic monitoring and magnetic field detection, allowing researchers to observe changes across multiple physical dimensions simultaneously. Once positioned, the sphere is set into motion at rotational speeds described in the range of 100 to 200 revolutions per minute. From this point onward, the experiment transitions from mechanical observation into continuous data recording across several sensor systems. According to the report, early results indicated unexpected internal thermal variation. Thermographic readings allegedly showed a gradual increase in internal temperature, rising from approximately 17 degrees Celsius to values in the mid to high 20s. What drew attention from the researchers was not only the increase itself, but the fact that it appeared localized within the structure, forming distinct regions of elevated temperature that expanded over time during rotation. In parallel, magnetic field sensors reportedly registered an increase in field intensity as the rotation continued. These readings were interpreted as evidence of dynamic electromagnetic changes occurring within or around the object during sustained motion. One of the most striking observations came from the load measurement system. During rotation, the sphere reportedly exhibited a gradual reduction in measured weight, in some instances on the order of approximately 300 grams. The system was configured to respond to such changes, and according to Garrido, when this threshold was reached, the apparatus automatically halted the experiment. At first, this behavior was treated as a potential anomaly or equipment malfunction. To test repeatability, the experiment was conducted multiple times under similar conditions. Garrido reports that the same general sequence of events occurred across 7 separate trials. Rotation begins, thermal and magnetic readings shift upward, a decrease in measured weight is detected, and the system stops once the threshold is reached. Given the consistency of the outcome, the team began considering whether the effect might be linked to experimental conditions rather than random error. To rule out mechanical interference or vibration-related artifacts, adjustments were made to the base structure to reduce movement and improve stability. However, the stopping pattern reportedly persisted even after these modifications, which further complicated initial interpretations. At this stage, the researchers shifted focus toward the internal structure of the sphere itself. Using inspection techniques typically applied in industrial component analysis, particularly those used for turbine parts, they examined the internal composition in greater detail. According to Garrido, this analysis suggested a highly symmetrical internal configuration resembling a cubic geometry embedded within the spherical exterior. This internal arrangement was interpreted as potentially significant in understanding how energy or fields might propagate through the object during rotation. From this observation emerged a working hypothesis that rotational motion may induce static electrical effects through frictional interaction, and that over time these effects could organize into structured electromagnetic patterns. In this view, continued rotation would not simply produce random electrical noise, but could encourage the formation of layered or coil-like field structures within the object. However, the researchers also concluded that the initial experimental conditions may not have been sufficient to fully develop or stabilize these proposed field structures. The rotational speed used in the early tests, 100 to 200 revolutions per minute, was considered potentially too low to generate the density or complexity of field interactions they believe might be necessary for a complete cycle of behavior. As a result, they proposed that significantly higher rotational speeds, potentially in the range of 700 to 800 revolutions per minute, might be required to observe whether a more complete or self-organizing pattern emerges. At this stage, the investigation moves from direct observation into predictive modeling based on the patterns they believe they are seeing. A key conceptual idea introduced in the interview is the possibility that the system could transition into a self-sustaining rotational state when certain conditions are met. Garrido compares this concept to thermodynamic systems such as turbine cycles, where external input is required only during startup, after which internal processes can maintain operation. Within this analogy, the sphere would require an initial external energy input, specifically mechanical rotation, to initiate internal field formation. Once these internal processes reach a sufficient level of organization, the system might, in theory, continue operating without further mechanical assistance. It is important to note that this remains a hypothesis within the framework of the experiment and has not been independently verified. The discussion also extends into the possibility that the device may be capable of transmitting and receiving signals. According to Garrido, the system has shown behavior that suggests signal emission, and future work aims to explore whether information can be encoded into these emissions. However, he also acknowledges a critical limitation. Even if signals are present, there is currently no confirmed method for decoding or interpreting any response that might be received. This introduces a further layer of uncertainty, shifting the interpretation from purely physical phenomena into the realm of signal analysis, though without established protocols or validated communication models. Given the reported behaviors, the researchers emphasize the importance of containment and safety measures. They describe the use of a protective enclosure designed to prevent uncontrolled movement, including the possibility, however speculative, of levitation or unstable motion. In theory, this enclosure could also be electrified to discharge accumulated effects and interrupt any cyclical behavior observed within the system. These precautions are presented as preventive measures rather than responses to confirmed hazards. At the time of the interview, the project remains ongoing. The team is reportedly working with engineering specialists to redesign and improve the experimental apparatus, with the goal of reaching higher rotational speeds and more stable measurement conditions. However, progress is constrained by funding limitations, which are described as the primary obstacle to continuing development. What remains from these experiments is not a definitive conclusion, but a set of repeated observations and interpretations that the researchers believe warrant further investigation. The data they describe suggest patterns that are internally consistent within their testing framework, yet still lack external validation or independent replication. As it stands, the Buga Sphere remains an unresolved case, situated between experimental anomaly, interpretive hypothesis, and ongoing engineering inquiry. Whether it ultimately reveals new physical principles or is later explained through more conventional mechanisms remains an open question.